Hello everyone, in this video we are going to see about how to implement a boolean expression using the NAND gates. Okay, let us see an example and then we'll find out how to replace all the gates using the NAND gate, because we are going to prove the universality of the NAND gates. So let us consider an expression f of a, b, c, d, e, which is the function with the 5 variables, and the output is a plus b bar plus c into d bar plus b e bar. So we are going to implement these functions using the NAND gate. For that, first of all, we have to find out the AND OR gates, because we know that basically we have all the AND and the OR operations are here. So we have to find out first the AND OR equation. So the first step is represent the Boolean expression using the AND OR gates. So this is the procedure to change the given function into an AND OR gate. So we are using this is the OR gate and this is the AND gate. So starting from here, a plus b bar plus c. So b bar plus c is one OR gate, and then d bar plus b e bar. Here this is d bar. For this OR gate, the input is d bar plus b e bar. Okay, and then how to get the b e bar from the AND gate b e bar. Okay, and so a plus, so a plus b bar c. So this is the b bar c, and this is actually b bar plus c, and this AND operator will give the b bar plus c into d bar plus b e bar, and this all these input is added to a. So all these inputs are processed, and the output is from here, and this is the term, and then this is added with the a plus. So a is the one input and these all terms are another input. They are given using the OR function. So first we are done. We have created the AND OR circuit for the given Boolean expression. Now let us see how gradually one by one we can change the AND and OR gates into NAND gates. So how to do, in order to, the second step is, in order to convert the AND gates into NAND gate, a bubble is introduced at the output of the AND gate, and to compensate the bubble, the input of the next gate is also introduced with a bubble. Let us see the diagram, we will be able to easily follow. So now this is the previous diagram, which is the AND OR implementation, and just this is the next diagram, which is done using the bubble. Actually, what this step says, if we want to convert the AND gate into NAND gate, we have to give the bubble should be given at the output of the AND gate, because we know that NAND is the combination of AND and NOT. So we have to first check for all the AND gates available. So this is one AND gate and this is one AND gate. So how to convert into NAND gate? Put a bubble in this AND gate output and one more bubble in this AND gate. So the diagram is drawn as this is one NAND gate and this is one NAND gate. If you introduce a bubble, this will change the meaning of it will change the value of the input. So in order to compensate the value, we have to add one more bubble to compensate. So this bubble we have added, and this bubble is compensated by adding one more bubble to the next level, because we know that any variable complement to the complement is the same variable. For example, x bar bar is x, a bar bar is a, so double bar is equal to the variable itself. So in order to compensate, how we have added a bubble, we are adding one more bubble in the other end also to compensate the values, and use one bubble. Okay, and this bubble is replaced by this bubble, and likewise for this AND gate we are made as NAND. To compensate, we are adding one more bubble in the same line, which will cancel the effect. So that's all the second step. We have converted to one step, converting all the AND gate into the NAND gate. While converting AND into NAND gate, the meaning of the variable may change, so we are compensating by putting one more bubble in the end of the line. So here two lines have this NAND gate, AND gate, putting a 0 over here and 0 over here. This to get complement or to get cancelled. So it is step 3. What does step 3 says is to impose uniformity at the input. If you get as one input with a bubble, the other input is also introduced with a bubble. Again, in order to compensate the bubble, the output of the preceding gate is introduced with the bubble or complement the literal. So how to show it pictorially? So now check for the output of this input of this OR gate. One is bubbled, other is not bubbled. If either of the one is bubbled, make other also bubbled. So we can see here a bubble is introduced over here. In order to compensate that bubble, now we are changing this A into A bar. Earlier it was A and now it is changed to A bar because A bar is the complement. So introducing one bubble here, we are compensating by changing the variable into A bar. So the meaning is not changed. And then coming to the next gate which has two inputs, one is bubbled, other is not bubbled. So how to do this? Add one bubble here and then to complement this input. Okay, so D bar is D. So when you add one bubble over here to just maintain the value, we are adding the one more complement in the variable. So D bar is D and the bubble is added. So this step 3 is completed just by introducing if one of the input is bubbled. That means if one input here, this one of the input is bubbled, make other also bubbled and accordingly make some changes in order to maintain the value. So this step is done. So we can see here gradually we are converting the NAND gate, AND gate to NAND gates now, and we are also making the OR as the bubbled gate. So next step we will see. Now if an OR gate is not having any bubble at either of the inputs, bubbles are introduced and are appropriately compensated as shown in the figure. So here why to invert the bubble in the OR gate is bubbled OR and then that will be the NAND gate. Okay, so now we have to bubble the OR gate, and if that output is bubble, it will become the NAND gate. So find out the OR gates. So this is one OR gate in which there is no bubble in the input. Other OR gates have already bubble. Using the previous steps, they have the bubbles, but this OR gate is without the bubble. So what you have to do, introduce bubble in both the places. So when you are introducing one bubble here, the input has to be complemented. So B bar is B. Likewise, when you are introducing 0 or a bubble over here, there is inverter in this input. This input has to be complemented. So C becomes C bar. So when you introduce the two bubbles here, it becomes C bar. Okay, so now the next step is also done. The step says that all the OR gate should have the bubble. So we have changed the bubbles in the OR gate and we are maintaining the values using the complement of the variables. So next step, what does Debongan's law says is A bar plus B bar is equal to AB the whole bar. So that is what we have just converted the values of the input is as a bubble for the OR gates in order to achieve this AB bar. So that will become the NAND gate. So now the diagram says here, now this bubbled OR is NAND. Okay, so replaced by NAND gate. This is bubbled OR is NAND. So replaced by NAND gate. So now we can see the whole diagram, everything becomes the NAND gate. So this is how to follow the steps and to convert all the gates according to the laws, and we have to convert the gates individually, whether it is an OR gate or bubbled AND gate, then finally we can get out the NAND gate. So this is the implementation of the function given previously. You can see that everywhere the NAND gates are here. So this is called as NAND implementation of the given Boolean expression. So even when you simplify the Karna map, after that we'll get some expression, and that expression can be implemented first, which is done using the AND OR function for SOP, and then everything will be converted into the NAND function. This is called as the NAND implementation of the Boolean algebra. So we have seen in the previous slides about the universality of NAND and NOR gates. Just a recall over here. If you want to convert a NOT gate, you have to give one NAND gate. For to make an OR gate, you have to do bubbled OR. Okay, so bubbled, so you are using the two inputs OR gate, and then this is also a AND gate. So these three will together form the OR functionality, and this sequence of two NAND will give the AND functionality. Same if a universality of NOR gates, a single NOR gate will give the NOT function, and two successive NOR will give the OR function, and these three NOR gate will give the AND function. So this is how to find out, wherever it is possible, how to convert the existing other tables into the NAND or the NOR functionality. So hope it is easy to follow, and thanks for watching.